Okay, so we're going further with this idea of approximations and the error we can approximate from them. I hope you can appreciate the fact that in science or engineering, um, you want to be able to estimate the error you get from certain amount of data, right? So if you know the position and the rate of change, then the error will depend on how big the acceleration can get, um, and then be able to write down exactly what's the worst case scenario and work with that. But you might come to a point where, well, we needed a certain level of tolerance and the error was too big. So is this approximation useless now? So that's what this topic is about, like how to do better and better approximation, um, although it comes at the cost of getting more data or doing more computation. So let's see what this idea is about. Okay, so um, we got an approximation from looking at the value of the function and its derivative. So what if we use higher order derivatives of the function? So like second derivative, third derivative, and so on. Let's take this idea one step beyond as before. Let's not look at just the function and the derivative, but look at the second derivative as well. So I want like a tangent parabola to this function cosine at x equals to 0. So let's take a couple of derivatives. So the first derivative is negative sine, and second derivative is negative cosine. And I want to approximate this at x equals to 0, so I'm going to plug those numbers in. So f of 0, f prime of 0, and f double prime of 0. So f of 0 cosine of 0 is equal to 1. Negative sine of 0 is 0. And negative cosine of 0 is going to be negative 1. So I want a parabola that matches this data. Right? So what do I want? So I'm going to call the second order uh, tangent, so Taylor approximation. So I want, let's look at it this way. So I want a parabola, so it's going to look like a quadratic function like this. And I want it to match this data, 1, 0, and negative 1. So let's take the derivative and plug it in. So t2 prime is going to be, so derivative of a is 0, derivative of bx is just b, and derivative of cx squared is going to be 2cx. And the second derivative is just going to be 2c. So if I plug in 0, if I plug in 0 for x, I just get a. If I plug in 0 into the derivative, this term drops out and we just get b. And if I plug in 0 in the second derivative, the second derivative is just constant, so it's just going to be 2c. So we could just read off what this has to be. So if I want to match the function at 0, a better be equal to 1, b better be equal to 0, and 2 times c should equal to negative 1. So c is equal to negative 1/2, I guess. So the tangent parabola at 0 is going to be 1 plus 0x minus 1/2 x squared. Okay, so cosine function looks something like this. Somehow this tangent parabola is the best approximation of the function near x equals to 0. Okay. Yeah, okay, it matches the first two derivatives. Okay, so in general, you can kind of see that if you see the pattern of what I got for the constant, linear, and quadratic terms, basically you just have to set it so that f of 0 is the constant term, f prime of 0 is the linear term, and f double prime of 0 divided by 2, because of the power rule, this is going to be the quadratic term, right? Okay. I'll just write that down there. So this is in general what we get. All right. So that's second order polynomial. And you could probably see where I'm trying to go with this. What if we use more and more derivatives, right? So we take more derivatives of this function, look at the third, fourth, and fifth derivative, and look at a longer and longer polynomial. And we just match all the derivatives. Like how far can we get? So you could probably kind of reverse engineer what's going to happen. So as you take more and more derivatives, you have to use power rule. So you're multiplying by the power each time. And to counterbalance that, you have to divide by factorials. So because we multiply by 2 here, we have to divide by 2 to make up for it, right? So if we had gone one more derivative further, because we had to use the power rule twice, so bring the 3 down and then bring the 2 down, you have to cancel the 3 and the 2. So 3 factorial. So 3 factorial is 3 times 2 times 1. And in general, for the coefficient for the nth degree term should have the nth derivative at 0 divided by n factorial. So that's going to be the pattern of the coefficient you have to put in front of each power of x. I hope that makes sense. All right. So let's see if we can do this for different functions. This is the important examples. So I think I'm going to do 3 examples. All right. So basically, we have to take any number of derivatives and kind of find a pattern. So the first derivative is going to be negative 1 over 1 minus x squared. And then by chain rule, I have to multiply by the derivative of 1 minus x, which is negative 1. So this becomes positive sign. For the second derivative, I have to use the power rule. So negative 2 minus x, and you have to subtract 1 from the power. So power was negative 2, now it's negative 3. And again, by chain rule, I multiply by negative 1, that becomes positive. And if I take the derivative again, so I have to multiply by negative 3. So 2 times 3 is 6, or maybe I'll just write 3 factorial here. And again, the negative sign will cancel out, so I'm not going to even write it. So maybe that's enough to get a pattern. Let's see, for the nth derivative. So it looks like for the third derivative, you have 3 factorial. So for the nth derivative, you're going to have n factorial in the numerator and 1 minus x to the power of n plus 1. That seems to fit the pattern so far. Okay, what if we plug in, so this is the derivatives themselves. We have to plug in x equals to 0. So if I plug that in, the derivative becomes, let's see, n factorial divided by 1 minus 0 to the n plus first power. So that's 1 to the n plus first power is just 1. So this is just n factorial. Okay. So if this is the derivative, remember the formula involves looking at the derivative and then dividing by n factorial. So in this example, I have n factorial divided by n factorial. All of the coefficients is going to be equal to 1 because the factorial cancels out. Okay, so all of the coefficient is 1. So the nth order Taylor polynomial is going to be 1 plus x squared plus x cubed all the way up to that x to the n. So it's kind of simple pattern to get. So that's for that function right there, 1 over 1 minus x. Okay, let's try it for the function e to the x. So this one, all the derivatives is e to the x. So the pattern's simple. And if I plug in 0, sorry, the nth derivative, if I plug in x equals to 0, we're always going to get e to the 0, which is equal to 1. Remember, the coefficient isn't the derivative. It's that divided by n factorial. So the nth order polynomial for e to the x is going to be 1 plus x plus x squared over 2 or 2 factorial plus x cubed over 3 factorial and so on. X to the n over n factorial. So this is going to be the nth order Taylor polynomial for exponential function e to the x. Just kind of note, 2 is same thing as 2 factorial. 1 factorial is 1. And it seems like it doesn't fit the pattern, but it actually does. 0 factorial is equal to 1 as well. So it fits the pattern there. For the 0th order term, the coefficient is 1 divided by 0 factorial, which is 1. Okay, all right. Let's look at the cosine. So cosine has kind of periodic derivative pattern, right? So the first derivative is going to be negative sine. The second derivative is going to be negative cosine. Third derivative is sine. And the fourth derivative is cosine. So it kind of loops back. So every 4 terms, every 4 derivatives, you come back to itself. So that's the pattern. Excuse me. And sorry, I'm kind of running out of room here. Let's plug it in 0. So cosine of 0 is equal to 1. Negative sine of 0 is equal to 0. Sine of 0 is 0. Negative cosine is going to be negative 1. And sine of 0 is equal to 0. So you could see now what's going to happen here. Every other term is going to drop out because the coefficient is 0. So this is the 0th term. So you get 1. The next term drops out. And then on the quadratic term, the second order term, we get negative 1 as the coefficient. So negative 1 divided by 2 factorial. And then on the third one, it drops out because the derivative is equal to 0. And then we're gonna have the pattern of just looking at the even terms because all the odd terms are either sine or negative sine, which just drops out to be 0. And all the even terms is going to be either 1 or negative 1. It kind of flips back and forth. So it starts with positive 1. And the next non-zero term is x squared over 2 factorial plus x to the 4th over 4 factorial. minus x to the 6 over 6 factorial, and so on. So x to the, yeah, well, I guess it's you're gonna go up until n, x to the n over n factorial, where n is even, right? Okay, so that's the pattern for cosine function. You can kind of imagine a similar thing for sine is going to take up all the odd terms because derivative of sine is cosine, and those terms will not drop out. Okay, all right. So these are the Taylor polynomials based at 0. If you want to have a tangent at some other value, x equals to b, you just have to kind of shift the formula to the left by b units. And this would be the general formula. Okay. So you're going to replace x to the n with x minus b to the nth power. So that would be shifting the graph to the right by b units. And instead of taking the derivatives at 0, you take the derivatives at b. So this would be the nth order Taylor polynomial at x equals to b. Okay. Okay. So hopefully these are better approximations than just using the one derivative and looking at the tangent line. So the question is, how does the error change as you look at these higher and higher order derivatives? So we're going to use, let's see what it's going to be, right? So this is a formula we had from earlier. We use the fundamental theorem of calculus and use integration by parts, okay? And this is the error portion on the right-hand side. So to compute the error for the second order Taylor polynomial, we use integration by parts again. So we keep taking the derivative of f double prime. So this would be f triple prime t dt. And the antiderivative of x minus t, again, I'm taking the antiderivative of t, but okay. It's also the antiderivative is x minus t to the squared over to negative 2. You can kind of reverse engineer. If you take the power rule, you'll get x minus t. Okay. So what do we get if we plug these into integration by parts? So this is the u part, and this is the v part, and minus integral of v. So I have x minus t squared here, and the negative 1/2. The negative will change the negative sign in front to a positive. And then du is going to be f triple prime t dt. Okay. And again, we do the same thing. So if you plug in x here, we have for t, x minus x will be 0. So that's what we get there. If you plug in b, we get b minus t squared, which is the same thing as x minus b squared. Sorry, no, we just get x minus b squared, and we have negative sign in front because it's the second limit that we're plugging in. And then for this portion, what we're going to do is we're going to make similar assumptions. So notice how this is the same thing as the second term in the second order Taylor polynomial. So if you bring this to the left-hand side, we get the original function minus the second order Taylor polynomial. And then error is described by this expression right here. Okay, and we're gonna use similar type of approximation. So suppose the third derivative is less than or equal to some particular constant m. We put the absolute value inside. F double triple prime is going to be less than or equal to some number m. And if we integrate this using the power rule, we're going to get that to the third power divided by 3. So 2 times 3 is going to be 3 factorial on the denominator. And this is going to be the formula for approximation for the quadratic or the second order Taylor polynomial. Okay, so if you can bound the third derivative, so we're looking at one derivative ahead, then the error is going to be bounded by this expression. So whatever constant you can use to estimate the third derivative, divided by 3 factorial times x minus b to the third power, and make sure to take the absolute value because we're looking at positive error. Okay, and you can kind of see the pattern here. If we keep doing integration by parts, you're going to get a similar formula over and over. So if you do the approximation up to the nth derivative, then the error for that Taylor polynomial is going to be, you first estimate the next derivative, so n plus first derivative by a constant, and the error is going to look like this, that constant divided by n plus 1 factorial, x minus b to the n plus 1 first power. Notice how the form of the error looks very much like the terms that you're adding in the Taylor polynomial itself. So you just remove the numerator, change that into a big M, and then the next term is going to be n plus first factorial and x minus b to the n plus first power with absolute value signs. Okay, so if you can remember the formula for the Taylor polynomial, the error, it's kind of like, it kind of looks like the next term you would have added if you took one more derivative. Okay. All right. So let's use this. Okay. So I'm gonna take the opposite point of view this time. So instead of specifying the approximation and giving an interval, and then asking like, what's the error going to be? I'm going to do the more practical thing and go backwards. Specify the error, specify the tolerance that you could use for your application. So let's say you want the error to be no bigger than 0.01. That's the worst case scenario. How many derivatives do I have to take to get this approximation? So that's what I'm going to work out. Okay, so this function natural log of x, we're gonna do the approximation at x equals to 1. So let's see if we can get the pattern here. So the first derivative is 1 over x. Second derivative is negative 1 over x squared. Third derivative is 2 over x cubed. Fourth derivative is going to be 2 times negative 3, so 6, or maybe 3 factorial over x, and then I think there's going to be a negative sign there. I don't know, is the pattern clear yet? Oops. Okay. So it looks like for the nth derivative, let's see, the numerator is not quite n factorial, it's n minus 1 factorial, right? Because for the fifth derivative, we have the numerator is 4 factorial. And the denominator is going to be x to the power of n. Okay. And let's see, we're approximating natural log of 1/2. So let's see, the n plus first derivative. Oh, also, let me actually move this a little bit. There was a negative sign here, or I guess it flips back and forth, right? So it could be positive. So what I really want to write is instead -1 to the n plus first power, I think. So when n is equal to 1, this would be positive. When n is equal to 2, 2 plus 1 is odd, so negative, it'll be negative and so on. So it'll flip the sign each time. Okay. Okay, so this is the n plus first derivative. So I have to come up with a constant m that's bigger than this. Okay, so I'm taking the absolute value so I can ignore this -1 to whatever power. So the negative sign goes away. In the numerator, I have n factorial. So that's going to be there. The denominator x to the n plus 1, that depends on the interval we're looking at, right? So we're looking at x equals to 1/2. But we were doing the tangent point to be x equals to 1. So let's look at the interval from 0.5 to say 1.5. So I'm always going to look at interval that's symmetric based at the point where it's tangent. So we're going to look at an interval from 0.5, which is 0.5 below 1, to 1.5, which is 1.5 above 1. I hope that makes sense. So this is the interval we're looking at. And what is the largest this derivative can get? Well, you get the largest derivative when the denominator is the smallest. So when x is equal to 0.5, we're going to have n plus first power here. Okay, and also we're going to multiply by x minus 1 to the n plus first power. Okay, let's see. Okay, I'm going to simplify this a little bit. Let's see, x minus 1 is going to be within 0.5, right? Sorry, we're looking at interval from the point where it's tangent, which is 1, and the furthest you can get, or the biggest difference you can get from 1 is going to be 0.5, because you're going 0.5 below and 0.5 above. So, okay, conveniently, we have 0.5 to the n plus first power. So this part cancels out with the numerator. And then the worst case, oh, sorry, wait, this is our m. Okay, and the error is given by this formula right here. So we have n factorial, which is m, divided by n plus first factorial. Sorry, I had already multiplied by this. That's what I did before. So m is actually, it was n factorial divided by 0.5 to the n plus first power. But this portion canceled out with 0.5 to the n plus first power that I just multiplied. Sorry, this was confusing. Okay. So the area is going to be given by n factorial divided by n plus 1 factorial, because everything else canceled out. N plus 1 factorial is same thing as n plus 1 times n factorial. So this thing cancels as well. Okay. And then what we're left with is 1 over n plus 1. Okay. And we want this to be less than 0.01. That was the error tolerance that we could that we want to live by. So what's the n that allows us to do this? Well, we could just compute it. All right. So if I multiply n plus 1 by both sides, okay, and then to solve for n, I'm going to divide both sides by 0.01 on both sides. And 1 divided by 0.01 is going to be 100. Okay, and then I can subtract 1 from both sides. Okay. So this is a lot of derivatives, but I guess we have the pattern, so it's not too bad. So we have to look at 99 terms on this series, sorry, the Taylor polynomial to approximate natural log of 1/2 to within 0.01 of the true value in the worst case. But it actually works for the entire interval from 0.5 to 1.5. Okay, I hope that made sense. Okay, this is where I want to end the video. I'll see you guys later.